Okay, we have two different masses that we've talked about. We've mentioned average atomic mass. We've talked about mass number. Mass number is a what? Whole number, right? It's that rounded whole number talking about just the protons and neutrons. It's a specific isotope that we're looking at. Average atomic mass we're going to find is a little bit different. So the question is, why are there decimals on the periodic table? Can you have part of a proton or part of a neutron? And I mean, they do break down, but in this class we're not worried about that. For all intents and purposes, it's no, right? You can't have part of a proton, can't have part of a neutron. Decimals, guys, are present because their masses represent the average of all the isotopes, and that's the key here, is that it's an average. All right? Page 6. This is kind of a recap from what we talked about yesterday, but we're going to be on page 6 at the very, very bottom of your notes on page 6. It's funny you asked that because I actually put it here on this slide, bottom of page 6. Yeah. I actually remember to do that. So, it's not just that it's an average, guys. It's a weighted average. Average atomic mass is a weighted average. It's the weighted average of the atomic masses of all the naturally occurring isotopes of the elements. Okay? It's based on carbon-12. Carbon-12 is kind of the poster child of kind of being, stationary and pure. When you look at the mass of carbon-12 on your reference table, it's like 12.011, I believe, because most of carbon, it's pretty much just all carbon-12. There's a couple other isotopes. There's carbon-13 and carbon-14. Have you guys ever heard of carbon-14? Carbon-14 dating? I would hope so. Maybe, maybe not. All right, we'll talk about that more when we do our nuclear unit later on. Our unit is AMU. We will have another unit later on in the year when we talk about molar masses, but we'll get there a little bit later on in about a month or two. Depends on two things. It depends on the mass, and this is specifically the mass of the isotope. Okay. And then the percent abundance. Okay. Where in your life have you guys used a weighted average? Where do you use a weighted average?
Grades.
Yeah, your grades, guys. Absolutely. Your grades in this class, right? Tests are 40% of your grade. Labs are 25. Quizzes are 25. And everything else is 10%. So they each have a different impact on your overall grade. That's exactly what we're doing here. The percent abundance is like the percent that you would see with your grades. And then the grade itself is like the mass of the isotopes. Have you guys ever calculated your grades before, like by hand in a class? Or you just kind of, whatever you see, you just roll with it. Be like, yeah, that looks about right. Did you? You kind of calculate it? Yeah, so maybe you haven't, guys. You could go ahead and do this. You could keep all your test grades in one group. Then you could have all your lab grades in another group, and all your quiz grades, and all your other grades, and just take them by their percentage and use this same process to calculate your grade by hand. Okay? Back in the day, before we had computers and things, before my time, all right, that's how your teachers would have calculated is by hand. Each section counts as a different weight. All right, so here we go. How to calculate? You're going to take the mass of each isotope. You're going to multiply it by the relative abundance and then add all the results together. You're going to convert the percent abundance to a decimal. So there's really kind of two ways that you can kind of solve this. Find the way that you are more comfortable with and go with it. What I mean by that, this is the general form, guys. You're going to take the isotope mass. Okay? Isotope mass multiplied by the isotope's percent abundance. Add it to the next mass and times its percent abundance. And keep doing that until you run out. It could be 2 isotopes. It could be 3. It could be 4. It could be 15. Okay? It depends on how much information you're given. Then, once you do that math, remember, follow your order of operations. Multiply first, then add them all up after you multiply them, then divide by 100. Okay? That's kind of the general thing. Now, many of you will like to do it the other way that I show, and that's dividing by 100 in the beginning. So instead of keeping these as percentages, if you convert the percents right to decimals off the start, you don't have to remember to divide by 100 in the end. I encourage you to do it that way. I'm going to show it that way because that's the way that I personally like better. I'll show both ways. You get the same answer either way. The only issue, guys, with doing it like this up here is remembering to actually divide by 100. You got to make sure that you do that. Now, the good news here with average atomic mass is this. I would star this and jot it down in your notes. You have a check to make sure that you've done it correctly. What do you think I mean by that you have a check to make sure that you've done your calculation correctly? Tony? If we look at the percentages, if we're calculating our percent abundance, which we'll do on Friday, yeah, all the percentages would have to add up to 100, but not exactly.
It should be close to 100.
Yeah, guys, you have a periodic table. When you do your calculation, you can go and look up what the actual average atomic mass is. So if yours is close, and what I mean by close is if it's within, 1 AMU, depending on, the ones that you have in your reference table, they are all the isotopes. In a problem, you're most likely not going to be given every single isotope. You're going to be given like the top 2 or 3 isotopes, so it's going to be close to what you find. But if you're way off, if you're off by 10 or 15, you've done something wrong. If you're within an AMU or 2, you know you've done it correctly. And that's what we're going to check. Check it every single time. All right? There's no time when you should do a calculation to calculate average atomic mass, that you're like left in the dust. Did I do it right or did I not do it right? Every single time you have that periodic table, go and take a look at it. Okay, you can check to make sure you've done it correctly. So let's just jump into an example here. This is the first one that's in your notes. It says, what is the average atomic mass for carbon if 98% is carbon-12 and 2% is carbon-14? So I highly recommend, you'll see me do this all year long. You've already seen me do it, guys. Keep track of your numbers. Bookkeep well. All right, so what I mean by that is, okay, we've got carbon-12. Okay, we've got carbon-12. That's our one of our isotopes. It is 98% abundant. So our percent abundance is 98. We have carbon-14. All right, it's 2%. Now, you can do it one of 2 ways. I'm going to show both ways here with the first one. It's kind of what I mean by it. You choose the way that you're more comfortable with, and then do it that way every single time. Okay? Naturally, you'll probably like one way better than the other. The first one I'm going to show is going to be like your notes show, like this slide back here showed. All right? So what I'm going to do is I'm going to take each mass, I'm going to multiply it by the percent, and I'm going to add all those up and then divide by 100 at the end. So here we go. I'm going to show my work. So I've got, if I look back, my mass is what I need first. What's one isotope mass that I have? Mass number that's talking about. What's one mass I'm given? Easy question. 12. All right, there's one. So here's my mass, my isotope of carbon-12. All right, what's the percent abundance for carbon-12? What's that? 98%. So I'm going to multiply it by my percent. Then I'm going to add any other isotopes. What's my other isotope mass in this problem? 14. I'm going to multiply 14 by its percent abundance, which in this case is 2%. Okay? Do I have any other isotopes? No, that's all I have. I've got 2 isotopes in this problem, so I'm going to cut it off, and then I'm going to set it up just like this, divide by 100. All right? So go ahead and do the math. 12 times 98. You will need a calculator, so if you don't have one, get up and grab one. What's 12 times 98? Just 12 times 98. I'm going to show all my work here for the first time. I think it's like 1176. All right. Plus 14 times 2. That I can do in my head. 28. Divide by 100. When you do all that math, so I'm just showing the steps here. I'm not going to do this for every problem. All right. 1176 plus 28. I believe you get something like 1204. Okay. When you add those together. All right. That's 1204 divided by 100. We should end up with 12.04 AMU. What do you see, guys, when we calculate that? When you go to your periodic table in your reference packet, what's the value that you have in your reference packet? 12.01. Are we close? Yeah, we're pretty close. Now, again, I told you before that, hey, there's a carbon-13 isotope as well, but these are the 2 most abundant. So we're close. We're only off by 0.03, 0.03 of a decimal. That means, guys, you know you calculated correctly. All right? That's what we're talking about by being close. If you're within half an AMU, you know you've done it right. I'm going to show you the other way. This is the way that I personally like better because I don't have to worry about that dividing by 100 in the end. What I'm going to do is when I see my percentages, I'm just going to convert these to a decimal right away. So this is going to be 0.98. Be careful when you have a single decimal. I would encourage you guys, as a double check method, to actually plug that into your calculator. Take the percent, divide by 100, and do it that way. Because a lot of people, when they see 2%, oh, it's just 0.2. No, is it 0.2? It's 0.02. So be careful with it if you're going fast. By converting these percentages to decimals first, I've effectively eliminated this times 100 piece, and I don't have to do that in the end. I did it in the front portion instead of on the back end. You with me? Okay, so now all I have to do is do this. 12 times 0.98 plus 2 times 0.02. The math, guys, you can see looks very similar. It's actually 11.76 plus 0.28, and when I add it up, I still end up with 12.04 AMU. Right? Either way, you get to the same answer. Whatever way you're more comfortable with, go with it and do it that way every single time. Okay? Some of you, half of you guys will probably want to do it, divide by 100 in the end. Half of you will probably want to do it in the front end. Okay? It's your call, but just make sure you don't do both. Okay? If you convert those to decimals, those percentages to decimals first, and then divide by 100, you're going to be off by a factor of 100. You do one or the other, not both. Questions? This is what you guys should have done in your lab yesterday with Beanium. All right, I hope that, does this seem familiar, the calculation, what you were doing? It should. All right, I want you guys to try the next one. Calculate the average atomic mass for bromine. As you finish up the problem, I'm going to start working it out so you can check your work up here on the board. Again, you may have done it the other way. I'm not going to show both ways here. I'm just going to do it one of the two. But again, the answer should be the same regardless of which method you use.
When we do this, we have to write out our formula.
The original formula? Nope, you can just plug it in. I want to see you plug into whatever method. That's the minimum. You don't have to write out just the original formula, though. You don't have to say like mass times percent plus. You don't have to do that. But I do want to see you kind of jot down the 2 or 3 or 4 isotopes and with their percentages, just so I know if, hey, I can give you as much partial credit as possible that way. So, when you set it up, whether you set it up like this or not, your final answer you should end up with should be what? What do you get when you do it? 79.9862. Obviously, that's more than what we would need to go to. I would, in this case, guys, I would round it to like maybe 2 decimals. Okay, sig figs I'm not really worried about with this. Okay. So I would call this like 79.99 AMU. What does your periodic table say for the atomic mass of bromine? 79.90. So are we close enough? Absolutely. Okay, again, there's other isotopes in there that we're not doing in this problem, so that's why yours is going to be a little bit different. Questions? Easy? All right, what I want you guys to do right now is you're going to complete page 1 through 6 on page 7 in your packet.